This question is asked in gate 23 of electronics. This is from digital subjects and from combinational circuit topic. The question is, in the circuit shown below, P and Q are the inputs. The logical function realized by the circuit shown below is. So it's a very simple standard 2x1 multiplexers, right? In a 2x1 multiplexers, the output expression Y is defined as S bar I naught. So if S is select line plus S I1, right? So here this S is connected to Q. So I am replacing S by Q. So that is, it is Q bar and I naught is connected to ground, right? You can see here I naught is connected to ground. Ground is nothing but 0 volt, or which is equivalent to logic 0 by default. Similarly, S, if I am replacing it by Q, this is Q and I1 is basically P, right? So your I naught is 0, I naught is 0 and your I1 is P, right? So Q bar dot 0 is 0 and Q dot P is equivalent to P dot Q. So this happens to be PQ. So Y is equals to PQ is the right answer, which is option A. This question is asked in gate 23 of electronics. This is from digital subjects and from sequential circuit topic. The question is, the synchronous sequential circuit shown below works at a clock frequency of 1 GHz. The throughput in megabits per second and the latency in nanosecond respectively are. Okay, so two parameters we are supposed to find. What is the throughput in megabit per second and what is the latency? So what is the meaning of latency? Latency meaning is what is the delay? Okay, what is the delay involved in these circuits? And what is the meaning of throughput? Throughput means in a second how many bits you are receiving an output. So that is what technically we call is a throughput. Let's say in a second I am getting 10 bits at this terminal. I will say that the throughput is 10 bits per second. So in simple language, what is the delay in the circuit? That is what latency. And how many bits you are receiving at output terminal in a second? That is nothing but your throughput. So let us do this. And it's a very standard circuit. And what is this structure, student? This is nothing but a serial in, serial out shift register, if you remember, right? Because only D flip-flops are used in cascade. It is nothing but a serial in, serial output register. So now, in this case, what is the delay involved? In other words, if I give a 3-bit data, because a 3-bit structure, I am speaking about 3-bit data, how much time you need to store a 3-bit data in these structures? 3 clocks. In an n-bit SISO shift register, you need n clock to store the data. So the delay involved is n into t clock. So because the clock frequency is 1 GHz, the clock cycle, what is the duration of one clock cycle? 1 by 1 GHz, which is nothing but your 1 nanosecond. So naturally, the delay or latency involved in a SISO shift register is n into t clock. So n is the number of flip-flop, which is 3, into t clock is nothing but your 1 nanosecond. So basically this is 3 nanosecond. So the latency involved is 3 nanosecond. So this is the one part of the question and the other part is throughput. Okay, so that is fine. But what about throughput? How to calculate throughput? See students, in a steady state, okay, when sufficient bits are being pushed at the input terminal, then what is going to happen? How does this work? Because you have only one input terminal and you have only one output terminal. So in each clock, okay, 1 bit data you will be receiving at the output terminal. But suppose, for example, now the content of the register is 101. Now if you give one clock cycle, what is going to happen? This 0 will be shifting here, this one will be coming here, next bit will be coming here. This pattern happens. In other words, in one clock cycle, 1 bit will be transferred to the output terminal. So in other words, in one clock cycle, 1 bit will be received on the output terminal. So in one clock cycle, in other words, in 1 nanosecond, one clock cycle is equivalent to 1 nanosecond. In 1 nanosecond, 1 bit data is received. So in 1 second, how much data will be received? So this is 1 into 10 raised to power 9 bits. These many bits will be received. So this is nothing but a throughput. So 10 raised to power 9 can be written as 10 raised to power 3 into 10 raised to power 6 bits. So this is nothing but your 1000. Okay, 1000. This is megabits. Yes or no? So in 1 second, these many bits will be received, which is equivalent to 1000 megabits. So the answer is naturally throughput is 1000 and this is 3. So the answer is 1000, 3, which is given by option A. So A is the right answer for this question. This question is asked in gate 23 of electronics. This is from digital subjects and from data converter topic. The question is, the signal to noise ratio of an ADC with a full scale sinusoidal input is given to be 61.96 dB. The resolution of the ADC is. So you study these things either in the PCM topic of communications, or even if in the data converter topic also we study this, like what is the signal to noise ratio. So this is based on a standard formula. The signal to noise ratio of a n bit ADC is given by 6.02n plus 1.763, this much of dB. So this is given as 61.96. So 6.02n plus 1.763 happens to be 61.96. So we are supposed to find the value of n in this case. The resolution of the ADC is how many bits they are asking. So very simple. So n happens to be 61.96 minus 1.763 divided by 6.02. If you check it out, so this is approximately coming as 10. So this is definitely, the answer is 10 bits. This question is asked in gate 23 of electronics. This is from digital subjects and from sequential circuit topic. The question is, for the circuit shown below, the propagation delay of each NAND gate is 1 nanosecond. The critical path delay in nanosecond is. So basically critical path delay means what is the worst case delay we are supposed to find. Now let us try with some inputs and let us try to find what can be the worst case delay. The delay can be worse if the delay of these both gates will be involved, right? So let us assume that initially the condition of this is 0 and 1, okay? So this is the initial condition I am assuming. You can assume anything else. So and then let us assume that the input which I am giving to this AB is A is 0 and B is 1. Why I am assuming like this? Because if this A is 0, then naturally in steady state this will be 1 and this will be 0. I mean the state which I am assuming 0, 1, it will be complemented. So whenever the the states are being changed, so we can expect like the worst case delay, because then only if you are getting the change in both of the state 1, 0, it means that the delay of this gate and this gates are involved. Then only you are getting the change in outputs, right? That's why I am selecting the input as 0, 1. And this initial condition also, let me assume 0, 1. Or if you take it is 1, 0, you select the input in such a way that it will change to 0, 1. No problem. So let us assume that this input A equal to 0, B equals to 1, we are applying at t equal to 0 nanosecond. Now, so if I am assuming Q equal to 0, so that means this is 0, and if I am assuming Q bar is 1, then this is 1. So this is what is the exact scenario at t equal to 0 nanosecond. At t equal to 0 nanosecond, this is what the exact scenario is. So naturally now what is going to happen then? Now, so if we are applying the input at t equal to 0 nanosecond, now the input to this gate is 0, 1 and the input to this gate is 1, 0. So naturally, because their delay are same, so the moment when they receive at t equal to 0, so this gate will produce output and this gate will produce output simultaneously. At what time? At t equals to 1 nanosecond. At t equal to 1 nanosecond, so this state which was 0 earlier, 0, 1 will be processed and this will be 1. This state which was 1 earlier, 0, 1 will be processed, this will be again 1. So this is the situation at t equal to 0 when I have applied the inputs. Now the state has changed to 1, 1 and this is the situation at t equal to 1 nanosecond. Now the point is when this is changed to 1, 1, so naturally this 1 is there, means this will be no more be 0, this will be 1 and this is the same 1. Now again this will be processed. If this is processed, 0, 1 if it is processing, this will be again your 1 and 1, 1 it is processing, it will be again your 0. Now this change, this 1, 0, okay, this you are getting at what time? You are getting this at t equals to 2 nanosecond. Here afterwards this is stable. In other words, if this is 1, you can see this is 1 and if this is 0, you can see this is 0. So it is latched actually. I mean this is equal to this feedback inputs and this is equal to this feedback inputs. So here afterwards there is no change. So at steady state, that is at t equals to 2 nanosecond, this is constant, or in other words, if the initial condition was 0, 1, we got this steady state 1, 0 at t equal to 2 nanosecond. So naturally the critical path delay or the worst case delay is 2 nanosecond, because beyond this it is not taking any extra time to get settled down. So you have a fresh set of inputs. With respect to this fresh set of input, after how much time we are getting these stable outputs. So that is basically 2 nanosecond here. Okay, and I have selected this input so that we can easily observe it. It may happen, let's say you are taking the input 0 1 and again you are giving the input as let's say you are giving the input as 1 1 for example, which is corresponds to memory state. In that case you may not observe any change. So I have selected the input and the initial condition in such a way that both of the gate will produce their outputs and we can observe the corresponding delay. Okay, so very simple, the answer is 2 nanosecond. This question is asked in gate 23 of electronics. This is from digital subjects and from data converter topic. The question is, a sample and hold circuit is implemented using a resistive switch and a capacitor with a time constant of 1 microsecond. The time for the sampling switch to stay closed to charge a capacitor adequately to a full scale voltage of 1 volt with 12-bit accuracy is dash microsecond. So first student, what data is given and what they're exactly trying to ask, let us understand. So you see a sample hold circuit implemented using a resistive switch and a capacitor with a time constant 1 microsecond. How does the circuit it should be then? So you have a switch like this, it's a resistor and it's a capacitor. So this is what the general architecture we usually study. So this is what is the sample and hold circuits, and this is applied to a what ADC. It's a 12-bit ADC. So it's a 12-bit ADC. And what is the full scale value of this? The full scale value of this is 1 volts. So it's a 12-bit ADC and its full scale value is 1 volts. And this is what is your input voltage V in T, and this is what is your capacitor voltage VCT. So this is R and this is C, and it is given that RC product, time constant is RC product is 1 microsecond. Yes or no? So now we need to understand what they are trying to ask. So the first part is clear. So based on this first part, I have drawn the circuits. So you see, then they're asking the time for the sampling switch to stay closed. So for how much time this switch should be closed such that, okay, to charge a capacitor adequately to a full scale voltage of 1 volt with 12-bit accuracy. What is the meaning of it? The meaning is, so if I am applying here 1 volts, how much time this switch should be closed so that the capacitor will be charged to a value which is of 12-bit accuracy. It means that first we will be calculating what is the resolution of this particular ADC. So how do you calculate resolution? So resolution is calculated using full scale value, which is 1 volt here, divided by 2 raised to power n minus 1. In this case, it is 1 volts divided by 2 raised to power 12 minus 1. If you evaluate this quantity, this is coming as 244 into 10 raised to power minus 6 volts, or 244 microvolts. 244 microvolts. This is what is the resolution of this, 244 microvolts. Now what they're trying to ask is, how much time this switch should be closed such that if this V in T is 1 volts, the capacitor should be charged to at least 1 volt minus 244 into 10 raised to power minus 6 volt. That is what is the meaning of accuracy of 12 bit. So ideally speaking, if 1 volt is given, so if you write the first order equation of capacitor voltage VCT, so it takes infinite time to charge up to 1 volts. But we are not interested for 1 volt, we are interested for this much of volts. For how much time this should be closed so that if the input is 1 volt, the capacitor will be charged to this volt. That is what the question is. It's a standard first order circuits, and in this case the capacitor voltage given by VCT is equals to Vc infinite into 1 minus e raised to power minus t by tau. So this equation we can simply use here. So VCT, so how much voltage you are expecting? We are expecting this much of voltage. 1 into 244, sorry, 1 not 1 into 1 minus 244 into 10 raised to power minus 6. This is what we are expecting, is equals to Vc infinite. Vc infinite is 1 volt, because if you are connecting here 1 volts at t equals infinite, assuming switch is closed, this will be definitely 1 volts. So this is 1 volts into 1 minus e raised to power minus t into tau is 1 microsecond, right? So RC is nothing but time constant. This is 1 into 10 raised to power minus 6. So from this we can easily get the corresponding value of t. So that is my answer. So this implies I can tell that 1 minus 244 into 10 raised to power minus 6 minus 1, okay, is equals to minus e into minus t by 1 power minus 10 6. This one I'm taking to this side. So this, you simplify this. If you multiply, okay, fine. So now if you multiply minus 1, so this will be plus and this is minus. Okay, then so you take this, so that is minus t divided by 1 into 10 is to power minus 6 is equals to ln of, if you take this one inside, so how much you get? So you get this is minus 1 plus 244 into 10 is to power minus 6, and you get this is plus 1, right? So this implies t is equals to minus 1 into 10 is to power minus 6 into ln of, these and these are cancelled out, it is 244 into 10 is to power minus 6, right? So take a calci and simplify this. If you solve for this t, so this is coming as 8.37 microsecond. So this will be the answer. That means if this supply voltage is 1 volts, if I am closing this switch for 8.37 microsecond, then this capacitor will be charged to this much of voltage. That was asked. So the time for closing for switch is 8.37. So answer is 8.37 for this. This question is asked in gate 23 of electronics. This is from digital subjects and from sequencer circuit topic. The question is, in a given sequencer circuit, initial states are Q1 is 1 and Q2 is 0. For a clock frequency of 1 megahertz, the frequency of signal Q2 in kilohertz is. So we are supposed to find the frequency of this signal Q2. So it's again, students, very standard model questions. You have to, it's a counter basically, you have to find the counting pattern, and then by finding the mod number, you can easily find out what is the answer. So for this, what we'll be doing is, so as usual, we'll be making the table. So the first factor in the table is what is the present state. Next, what is the flip-flop inputs. And next is what is the next state. So there are two flip-flop we have. So present states are Q1 and Q2. And flip-flop inputs, these are, if you see, D1 and D2. So what is D1? D1 is connected to, if you see this one, this is Q2. So D1 is connected to Q2. So here I am writing this is Q2. And D2, if you observe, this is Q1 bar. So D2 is connected to Q1 bar. So this is your Q1 bar. And next it is Q1 plus, and this is Q2 plus. So first let us write the combination of these present states 0, 0, 0, 1, 1, 0, 1, 1. So based on this, we can now easily proceed. So if I ask you what is the flip-flop inputs, so D1 is Q2. So Q2 column I'll be copying as it is, which is 0, 1, 0, 1. And D2 is Q1 complement. So complement of this column 0, 0, 1, 1 become, if you take complement, 1, 1, 0, 0. So now you know the flip-flop input, you know the present state, you have to get the next state. So you have to make use of state table. And for a D flip-flop, Q plus equals to D. So what is Q1 plus if I ask you? So Q1 plus, because it's a D flip-flop, it is simply D1. If it would have been a T flip-flop, then TX or Q, like that I would have gone. And similarly, Q2 plus, it is simply D2. So this D1 and D2 I'll be simply copying here. So D1 is 0, 1, 0, 1. D2 is 1, 1, 0, 0. Now you see the initial state is given 1, 0. This is the initial state. So if the initial state is 1, 0, if you observe this, from 1, 0, where this is going? It is going to 0, 0. So from 1, 0, it is going to 0, 0. Now from 0, 0, where it is going? From 0, 0, it is going to 0, 1. And from 0, 1, where it is going? From 0, 1, it is going to 1, 1. And from 1, 1, where it is going? It is going to 1, 0. So 1, 0, like this. So from this counting pattern, we can easily see it's a mod 4 counter. It's a mod 4 counter. And we are supposed to find the frequency of Q2. If you observe this Q2, this is what I am writing. This is for Q1, Q2, right? Q1, Q2. So if you ask me what is the pattern of Q2, Q2 pattern is 0, 0, 1, 1, right? 0, 0, 1, 1. Again 0, 0, 1, 1. Again 0, 0, 1, 1. This is what the Q2 pattern is. So we can see, like in every 4 cycles, this pattern is repeating, right? So it's overall a mod 4 counter, and to be very specific, if I ask you regarding Q2, so naturally it has to be again the same mod 4 counter. So if it's a mod 4 counter, the frequency is, f of Q2, it will be clock frequency divided by the mod number, which is 4. So clock frequency is given as how much? 1 megahertz. So 1 into 10 is to power 1 megahertz into, I will divide by 4, which is 0.25 into 10 is to power 6. So this is 250 into 10 is to power 3. This happens to be 250 kilohertz. So this is supposed to be 250. It's a mod 4 counter, right? And that to be, it's a synchronous counter, not asynchronous. So synchronous counter means we do expect the frequency to say. Otherwise, to be very specific, you can observe in how many cycle the Q2 pattern is repeating, because you are supposed to give the answer of Q2. In 4 cycle, Q2 pattern is repeating. In 4 cycle, if Q2 pattern is repeating, so naturally its frequency will be clock frequency by 4, which is coming as 250 kilohertz. So the answer is 250 for this.